Greetings, YouTubers. Welcome to another episode of Vessel Voyeurism. Actually, this video is part 6 in a series on backpacking stove efficiency. And they build on each other, so far covering everything from pot diameter and flame level to wind effects, wind screens, and heat exchanger systems. So I always recommend you watch them in order. Today's topic is one that I've been asked about multiple times. Is there a difference in fuel efficiency between pots made of titanium, stainless steel, or aluminum? While it's still boiling season, I thought I'd look into it. Now, my methodology has been described in detail previously, but for quick review, all tests are conducted inside my climate-controlled shop using precision instruments. I use a series of MSR low-down adapters preset to 3 different flame levels, low, medium, and high. This gives me consistent output test after test. And that gives me a static margin of error of just a few hundredths of a gram of fuel, which is fine enough to detect even subtle effects. For this investigation, all boils were done using an MSR Pocket Rocket Deluxe, and by boil I mean heated to 200 degrees. And this is more than hot enough to render water safe to drink, and it will make a cup of coffee or rehydrate a freeze-dried meal. See part 1 of the Backcountry Water Treatment series for a thorough discussion of boiling versus pasteurization. For volume, I use 415 milliliters of water. This fits nicely in a small container and is the amount needed to make most backpacking meals. We know from part 1 that vessel diameter can affect fuel efficiency, so for the testing lineup I did my best to find 3 pots of similar width, one each in titanium, stainless steel, and aluminum. Choices were limited, and that meant having to mix pots from different manufacturers within a group. This could at least potentially introduce more variables than desired. To get more than one look then, I put together 3 iterations of these groups, each in a different size range. For the small trio, we have an ever-new 750 milliliter pot in titanium. Mine came by itself, but apparently it's currently only available in this set. It looks also like they changed the lid. At the time, I had to order a cover separately, and this was it. For the stainless steel option, I went with the Self-Reliance Outfitters 25-ounce cup, which I refer to in all the charts as the Pathfinder 750. And for the aluminum member, we have MSR's 0.8 liter pot that came in this kit. I removed the rubber so as not to affect performance. And as you can see, they're all pretty close to the same size. For the medium trio, we have a Toaks Light Titanium 700 milliliter pot. This is part of their D115 collection. It comes in a wider format than their standard 750 milliliter, which is in the D95 series. I pulled the steel representative from Snow Peak's Personal Cooker 3 set. And the pot in GSI's Halulite Micro Duelist was the closest aluminum match that I could find. For the last trio, I went big. In titanium, we have a Toaks 1600. For steel, a Pathfinder 64-ounce bush pot. And in aluminum, I got an MSR Traillight 2-liter pot. And it's always at this point that I remind everybody I buy all my own gear through regular channels at full price. I don't get freebies, deals, discounts, or coupons, and I don't have sponsors or relationships of any kind with anybody. I measured all the containers, and for visual reference, here's what the diameter groupings look like. Not exactly the same sizes in each group, but pretty close, and the best that I was able to find. I also used a set of outside calipers to reach around the lip of the pot and get a read on material thickness. And you can see an obvious pattern here. Aluminum, which is easier to crush and to melt, needs to be made thicker for durability. The steels are in the 0.5 millimeter range, with some being a bit under. And much titanium ware is also pressed out of 0.5 millimeter, but both Toaks and Evernew offer ultralight models in their smaller sizes that run closer to 1/3 of a millimeter. So with all that in mind, here's a look at the results when using a low flame and the lids on. Starting with the smalls, we see what I think a lot of people anticipated. The vessel made of highly conductive aluminum was most fuel efficient. So for comparison, here's a chart of the thermal conductivities of each type of metal. Aluminum is several times higher than either of the other two. Titanium always gets knocked for its poor conductivity, but interestingly, Type 304 stainless, which is specifically used for the Pathfinder gear, comes in even lower. So technically, these results are in the order of conductivity, though the difference between titanium and steel is within the margin of error, so not significant. But aluminum coming in first place is actually the exception, not the rule. Note that for both the medium and the large containers, aluminum comes in second, being edged out in each case by a titanium vessel. I should point out that with the large pots, I took advantage of their volume to see what happens with twice as much water. So the numbers you're looking at reflect the fuel required to boil a double batch, that is 830 milliliters all at once instead of my standard 415. So that's why they're so much higher than all the rest. It was my hope that any subtle differences might be amplified by the longer burn time required for a bigger batch of water. And it may have played out. You can see that the ranking observed with medium pots is repeated with the larger ones, but with an even taller spread. Right, well, why would the more conductive aluminum pots need a greater amount of fuel to boil than titanium? Time to start pushing the ad hoc button. When aluminum is touted as a desirable material in cookware, it's because aluminum pans do a better job of avoiding the hot spots that will scorch your food. This is accomplished by the superior thermal conductivity, which helps spread the heat out across a greater area of the pan instead of just remaining concentrated in an extremely tight and hot spot directly at the point of contact with the flame. That's great if you want to avoid burning your pancakes, but is it necessarily better for fuel efficiency? So there's a fundamental principle in thermodynamics. The rate of heat transfer from one thing to another depends on the difference in temperature between them. The greater this difference, the faster heat will move. And you can see where I'm going with this. Those hot spots burn your food because they transfer heat from the pot into its contents faster. The lower conductivity of titanium doesn't mean its rate of heat transfer into water is lower per se. It means that heat within the titanium itself won't spread out as fast. That heat stays localized over the flame and it reaches higher temperatures than a pot made of something that spreads it out more quickly. A higher temperature differential between the pot and the water means faster heat transfer between the two, at least at those hot spots. To be sure, we've got ourselves into yet another circumstance of countervailing effects. The aluminum pot will have more squares transmitting heat into the water, but the titanium's fewer squares will be hotter and therefore faster transmitters. So which one ends up being more fuel efficient overall? It's the sort of thing best determined experimentally, and 2 out of 3 times it was titanium for the win. Now, there's no way that's the only effect in play. It's likely several going on all at once. But it is a way to make some sense out of how titanium might be aluminum in the boiling efficiency game. Consider that aluminum makes a good heat sink material. When you make a pot out of heat sink material, it isn't specifically designed to boil faster. In fact, it's built to keep the contents from heating up too quickly. That's great for cooking, but not particularly in boiling. Like I always say, I'm just here to provide you the data. My homemade conclusions are just for fun. Also, all of this speculation only explains these 2 results, not this one. I'm at somewhat of a loss regarding why this aluminum pot does better. And I retested it just to make sure, and the results were similar. The only thing I can think of is it's the smallest. At this diameter, even a low flame from this stove covers pretty much the entire bottom in blue flame. But with the wider pots, there's more area further out into which the heat can sink away. And yes, heat can sink up into the sides of the pot, but wider pots also have sides. There's still more mass in the heat sink of a bigger pot. You've got to fill up these bigger reservoirs of heat before you can start to get efficient, high differential transfer into the water. Like I said, just one take on what are multiple valid points to be made. You guys always have interesting ideas that did not occur to me. I also ran everybody through using a high flame. Now you can see that aluminum wins in all 3 sizes. I kind of think that this is consistent with my heatsink hypothesis. At the higher flame rate, heat has a better chance to build up faster than it can dissipate, and this allows hotspots to form more effectively. And since there's a limit on how hot those spots will get, extra heat will serve to spread their area into an even greater amount of high efficiency transfer points. There's definitely room to argue about all this though, so feel free to have at it. One other thing that the keen-eyed among you may have spotted, with a fast flame, the stainless steel Snow Peak beat both of its counterparts, titanium and aluminum. And I retested this result as well and verified it is real. So we've got an effect that didn't show up with a low flame, but does manifest on high. And I'll get the speculation ball rolling, and then leave it to you. Why is the speculation ball made of rubber bands? I don't know. Okay, here's my theory. What makes the Snow Peak pot stand out from the crowd? It's not really its diameter, its thickness, or even the material. Have a look and tell me what you see. Shiny. When I was a wee skeptic, I asked my dad, how come a wrench sitting on the driveway in the sun got so much hotter than a screwdriver handle that had been out there the same amount of time? He looked over from whatever it was that he was inventing at the time and said, oh, that's because of the A over E. Because, you know, an 8-year-old would know what that means. Well, what he was referring to was the absorptivity over the emissivity. Any object will theoretically reach equilibrium where the heat coming in matches the heat radiating back out. At what temperature that equilibrium is reached will depend on the A over E. An object with low absorption and high emission will stay relatively cool under a given amount of thermal radiation. But something with poor emissivity will accumulate more heat, reaching a higher temperature before finally tapering off into equilibrium within its current environment. The lower the emissivity, the lower its rate of radiating accumulated heat back away. So take a look at some emissivity coefficients for different kinds of steel. I'll put these into a graph so you can see how they compare in scale. In the middle you have a fairly common type of stainless steel. Next to it is a stainless steel that has been weathered. You've also got galvanized steel when it's both new and old. And over here, this tiny little emissivity belongs to stainless when it has been polished. Again, I don't know what I'm talking about, but it seems suspicious to me that the conspicuously shiny pot suddenly outperforms its peers under heavy heat load. Now, some might say that the polished surface should be reflecting heat more, helping the pot resist warming up. But reflection is for radiative transfer, and that's not how pots heat up in these tests. They get conducted heat from direct contact with hot flame. So my point is that you have to remember there's always two sides to the equation, in and out. Internal temperature is based on the balance. So as the pot heats up, it begins giving that energy back away faster and faster via radiation. But if you turn down its ability to radiate, it will heat up faster. That's what a lower emissivity does. Beyond that, I'll leave it to you. Personally, I don't do hot drinks. I'm usually just cooking for myself, so I only need one batch of water for my freeze-dried meal. But a lot of people might want two. So instead of just preparing one batch at a time, I was curious about the efficiency of using a larger pot and boiling twice as much water at once. And we've actually already seen the answer. The results are here with the large trio of pots, where I used 830 milliliters instead of the usual 415 milliliters. And these are just the raw fuel use numbers. It's a bit of an apples to oranges problem that keeps the answer from being immediately obvious. So I created this batch normalized version of the chart. Now you can directly compare the fuel costs per the same size batch of water. And as you can see, boiling two batches at once was cheaper than two separate boils, regardless of whether the pot is made from titanium, steel, or aluminum. Now, obviously, I did a whole video about how diameter can affect efficiency, so you might suggest that the fuel reduction is due to the wider pots. But recall from part one, that's really only with a medium or higher flame. On low, the chart was basically flat across a very wide range of pot diameters. A small hotspot directly over the flame was doing all the work, and it doesn't really matter how much extra pot you have on low. To me, this leaves efficiencies of scale as the best explanation for the fuel savings observed. Well, how much of a benefit are we looking at? Here's the number of water batches you can boil for each scenario. With titanium, you can actually get 2 extra batches of hot water out of a small gas container, if you boil them 2 at a time. For aluminum, you can get 1 extra boil over the next best option. And with steel, while there was a numerical improvement in fuel efficiency, it wasn't enough to get another full boil out of a 110 gram can. Regarding a high flame, here are the batch normalized results. Note that the fuel savings from double batching your water are even greater here than they were on low, relatively speaking. You're still wasting fuel by using high, but if that's how you roll, it becomes even more worth it for you to boil twice as much, half as often. And the number of boils on high. Now remember, on low you could get up to 21 boils from a small can. By cranking up the heat, you're actually losing the opportunity for as many as 5 hot meals from just 1 canister. While I had everything set up, I decided to try a couple of unique container types as well. The Bear Bowl is a folding plastic vessel mounted on an aluminum plate. A collapsible stove-worthy container is a nice idea, but I've always wondered how well the heat transfer would work. Sea to Summit made the X-Pot line of collapsible bowls and cups. I have the 1.3 liter kettle. The bottom is aluminum and the sides are heat-resistant silicone. Unlike the origami nature of the Bear Bowl, an X-Pot pops up and down pretty quickly. It looks like Sea to Summit has modified and renamed the line. Currently they offer a Frontier kettle in a slightly smaller size. And then lastly, with an eye towards the inevitable discussion of weight efficiency, I pulled out my Toaks D130 pot in the 900 milliliter size. And the pots I used for the large trio are bigger than they need to be for holding a double batch of water. And this is the lightest container I could find that would still be able to hold the 830 milliliters for an ultralight double batch comparison. And here are the combined results with the new pots alongside the ones you've already seen. And these are the raw fuel numbers for both the single and double batch tests. Yep, you are seeing that correctly. I used a single batch of water with the Bear Bowl, yet it required almost as much fuel to boil as some of the double batched containers. And it becomes even more obvious when we look at the batch normalized view. So clearly there's an issue with heat transfer in this design, probably owing to some gapping between the aluminum and the plastic. Also, this plate is 2 mils thick. To keep the plastic from melting outright, they've mounted on what is effectively a heat diffuser plate. Once again, my heatsink hypothesis is suggesting all that scorch protection hurts fuel efficiency. Another interesting surprise was that the X-Pot with a double batch of water technically ended up being the efficiency champ. Though it's effectively tied with the titanium pots from Toaks, it outperformed every other aluminum option. Should I say it? I'll go ahead and say it. Even though I don't think the sides matter as much as the bottom, without aluminum sides, the heat in the bottom will have less ability to sink away, letting the bottom temperature rise disproportionately to a conventional pot, aiding in faster heat transfer. Heat sink hypothesis. Oh, and by the way, I knew that some people would not be satisfied with my dismissal of diameter being a factor with the larger double batch pot tests, even with the low flame. So while I was testing these new pots, I did some back-to-back direct comparisons of the same pot under both single and double batch conditions. And here are the normalized results. With both the X-Pot and the Toaks 900, it is indeed more efficient to boil 2 batches at once. Okay, it's time for somebody's favorite part. Here are all the various pot weights shown side by side. Yeah, that's not a suppressed zero. There's just that much difference between them. So in fairness, these weren't picked with weight specifically in mind. Some have bales and handles, while others are just plain cups. And as mentioned, some of them are larger than absolutely needed for the batch size tested. They were chosen to be roughly size matched by material in each of their respective groups. While diameter doesn't matter much with a low flame, it probably does bias the results on high. So as far as lids go, here are the weights of the manufacturer supplied options. You can of course substitute your own or make one out of foil. So in part 5, I built a simple calculator for evaluating the relative weight efficiency of two different options. It's available along with all the data and graphs from the entire series in the free downloadable spreadsheet, linked in the description box below. It's there so you can more easily compare the systems that interest you. Here are a few of the ones I was curious about. For the folks interested in a compact but efficient single batch system, I compared the lighter Evernew 750 to the more fuel efficient but somewhat heavier MSR 0.8 liter cup. You save 26 grams with the Evernew but need almost a quarter gram of extra fuel per boil, which nets you one less boil from a 110 gram canister. Compared to the pot weights, however, the fuel savings are relatively small. It would take 113 boils with the more fuel-efficient pot to make up for its added weight. Given that there's only 18 boils per can, you'd have to be on a trip requiring you to carry more than 6 of these all at once before the savings become worth the wait. So looking for some of the best compromises between fuel and weight efficiency, we have these two. The Toaks 700 was the most fuel-efficient single-batch pot, and it also happens to be the lightest. And put that up against the Toaks 900, which turned out to be the lightest and most fuel-efficient of the double-batch containers. It costs you just 19 grams to get a pot big enough to do 2 batches of water at once. When using it to boil a double, the 900 saves you about 1/3 of a gram of fuel per batch. That is compared to the 700 doing 2 separate single boils. And that'll get you 2 extra hot cocos with the bigger pot. Still though, it takes 54 boils to make up for the weight. And since there's only 21 boils per canister, it won't be worth it unless you're on more than a 2-can trip. So, use the calculator, compare it to your heart's delight. The last one I'll show is for those curious about the ultralight standard from previous videos, the beloved handleless Toaks 550, compared to the 700 that was tested here. Because the fuel efficiency difference is so slight, you can save 18 grams and keep the same number of boils per 110 gram can. Okay, I believe that makes it time for the summary. While they aren't huge, there do appear to be measurable differences in the fuel efficiencies of different pots. And there are, with one exception, some patterns related to pot material. Within each size class, stainless steel was always least efficient. Generally, that is to say 2 out of 3 times, titanium actually required less fuel to boil than aluminum. And this flies in the face of the belief that a metal with higher thermal conductivity should result in higher fuel efficiency. And clearly that doesn't have to be the case. It might be that aluminum's superior conductivity only serves to make the pot itself a better heat sink, thereby reducing slightly the transfer rate into the water by preventing the hot spots that actually transfer heat fastest. That's merely my own speculation, however. Other plausible theories exist. Also, the small pots were an exception. Their aluminum was the most efficient. Your guess is as good as mine regarding why that might be, but I did test it twice to verify. It might be that a smaller pot has less ability to sink away heat from the flame zone. Heat sink hypothesis. It could also be that this pot was the widest in its group. I don't think that diameter matters much on a low flame, but to the extent that it does more so with smaller pots than larger ones because of diminishing returns. Maybe there's something special about this alloy. Thermal conductivities can vary between types of aluminum. Does the dimpled bottom matter? It could always be that multiple factors are simultaneously providing small effects that add up. Now, on high, aluminum wins every time. With a sufficient rate of heat input, the liability of heat sinking can be overcome. We also saw an anomaly with the stainless steel snow peak. It's likely that emissivity plays a role here, with the polished steel having a remarkably lower coefficient than other types. We also saw that per batch of water, boiling 2 batches at a time was more efficient than individual boils for each type of pot material. This was confirmed with some direct comparisons of single and double boils using the same pot. A look at some collapsible pots showed some very different results. A bare bowl takes almost twice as much fuel to boil as the rest, probably due to heat transfer issues with the plastic to aluminum interface. The X-Pot kettle, however, was technically the most efficient option when boiling doubles, though it's effectively tied with the 2 titanium competitors. The smallest, lightest pot I could find that will just handle a double batch of water was also one of the most efficient boilers. And while it won't be able to make up for its extra weight and fuel savings on trips requiring 2 cans of gas or less, it will get you an extra couple of hot meals out of one of these for only a 19-gram penalty, providing you need 2 batches of water at a time. For perspective, that 19 grams is the equivalent of this much water. Overall, while pot material does seem to make some differences in fuel efficiency, these are not as significant as their differences in weight. This, for example, is almost exactly the same weight as this. As always, I very much appreciate your time, and thanks for watching.